Next topic is proof by cases, which is a sort of sub-method which can appear in both direct and contrapositive proofs. It's a very important technique which you'll definitely make use of both in your direct proof and your contrapositive proofs. So, proof by cases. And so proof by cases relies on this very important equivalence, which tells you that if P or Q imply R, so P or Q imply R, then that implication is equivalent to the following pair of implications. P implies R and Q implies R. And so this means that if we have an implication where the hypothesis is a disjunction, an or of two statements, then we can prove this statement by proving these two statements. And so instead of proving something which might be difficult together as one blob, we can prove these two smaller pieces independently. And that gives us a proof of the whole thing. Okay, so now we can prove this particular equivalency with a truth table, which is doable. It's a bit tedious, but it's not too hard. Or we can prove it via equivalences, which is a good exercise. Indeed, it might be an exercise you get for homework in this course. Now, as I said, this is very, very useful because it allows us to split a hypothesis into separate cases. So as an example here, if n is a natural number, then n squared plus 5n minus 7 is odd. This is a perfectly good implication, which we'll prove in just a moment. And n being a natural number, well, that's the same as n is even or n is odd. We know that every natural number must be one of those two cases, and so we can split the hypothesis here into those two cases, implying our conclusion. And this result at the top here tells us that we can prove the equivalent statement, n is even implies blah is odd, and n is odd implies blah is odd. And so we break our proof of a single implication into two sub-proofs of those two implications, which are going to be easier. In fact, you should realize by now, okay, I've seen this sort of thing before. If n is even, it's 2k, blah, blah, blah. N is odd, it's 2l plus 1, so blah, blah, blah. You know how to do these pieces individually, where the original thing might be a little bit more difficult. And so we prove each case in turn, hence proof by cases. So let's look at this result. So, result. Let n be a natural number, no, let n be an integer, then n squared plus 5n minus 7 is odd. Okay, so let's break this into bits. So, as is usual, we have a direct implication. If n is an integer, then blah is odd. So we assume the hypothesis is true. That's very, very standard. So that n is an integer, and we know that n is either even or odd. Okay, so it breaks into two subcases. Now, let's make things easy for the person reading it and outline that we are actually doing two cases here. So I've actually put case 1, assume that n is even. Okay, so that's one of our two cases. Well, now we have a little sub-proof. When n is even, I know it's 2k for some integer k. So that means the polynomial we're interested in, I can write it out, and I can see that it's 2 times something, and that something is integer squared, this is all an integer, so it's 2 times an integer, so blah is odd. Okay, so this is pretty straightforward. It's just like what we did for a direct proof before. It's now just a sub-proof sitting inside our main proof. For case 2, again, I'm making it very, very easy for the person reading it to see that I'm breaking it down into cases, that I'm using proof by cases. So we're making life easy for the person reading things. And this goes very much the same way. Case 2 is now that n is odd. So I assume n is odd. So n is 2l plus 1 for some integer l. So again, we can show that it's 2 times something plus 1. So we know that this is odd. Okay, so we've proved our two cases, two sub-cases independently now, and we can put everything back together. We just tell the reader, hey, since this works in both cases, the result works, and we're done. Okay? So we break the proof into these two cases and remind the reader, hey, I'm doing case 1, I'm doing case 2, and then at the end, since all the cases work, everything's good. Okay? Now, proof by cases can be a little bit tricky, so should we watch out for a few things that can go wrong. So the first thing is, it's good to give the reader some context, to make sure you tell the reader that you're doing what you might call case analysis, that you're doing a proof by cases. Okay? This is just letting the reader know, so they don't get to the end of the proof and then realize, oh, that's what they were doing. The reader shouldn't have to do that. The reader should be able to look at the proof and just read the start, and you tell them, hey, this is what I'm doing. Okay, let the reader know what's happening. Now, a very common mistake is to make sure that you get all the cases, that you haven't somehow missed one of the possibilities in the hypothesis. This is a very common mistake, so you really have to think very hard about how does the hypothesis break up into cases. And indeed, in more complicated proof by cases examples, a case might break up into sub-cases, which break up into sub-cases, and so forth. So making sure you get all the cases can be a problem, okay? So you have to be very careful there. Now, what we can see, and indeed the last example showed us, is that sometimes cases are extremely similar, but you should be very careful of skipping steps, especially when you start out doing these proofs. Now, a term that gets bandied around a lot in this context is without loss of generality. So I'm going to do this case because the second case is going to be very similar. So you'll often see this without loss of generality contracted to W log. And this can be a very good source of errors, particularly when you're starting out learning to prove things. So be very careful using that phrase. And indeed, I discourage you from using it and skipping steps until you've got a bit more practice. And indeed, this without loss of generality, it's a good source of, it's a dangerous phrase in mathematics. And there's a lot of good dangerous phrases in mathematics, like without loss of generality. Clearly, this must be true. Obviously, this must happen. A quick calculation shows that. It is easy to show that. All of these things are basically, I'm going to skip some stuff. Okay? Don't do that, especially when you're getting started. Make sure you do everything carefully and slowly, and you can skip a bit of stuff when you're writing things up, but you definitely shouldn't skip things when you're doing your scratch work, when you're doing your draft work. Okay, let's do another example. So, let n be an integer. If 3 divides n squared, then 3 divides n. Okay, and if you think about this, you can convince yourself that this is true, but also this smells, oh, sorry, I've gone too far. Let me go back. What have I done here? This smells of a contrapositive proof. Okay, so if I flip this around, then this becomes, by taking the contrapositive, not the conclusion implies not the hypothesis. So 3 doesn't divide n implies 3 doesn't divide n squared. And now we're on firmer footing. Okay. Now recall Euclidean division, that fact that we had before, that every integer n can be written uniquely by considering what happens when we divide it by 3. In particular, an integer n is either 3a plus 1, or 3a plus 2, where a is some integer. Okay, so this is all it means from Euclidean division. So when we consider numbers divided by 3, we have to get uniquely one of these 3 cases. Now, since 3 doesn't divide n in our hypothesis now, since we took the contrapositive, we must either have n is 3a plus 1 or n is 3a plus 2. Those are our 2 cases. And so we can just explore what happens. Okay, case 1, if n is 3a plus 1, then n squared is blah. If n is 3a plus 2, then n squared is blah. And these are now standard direct proofs like the ones we started off doing. And so this is much, much easier once we break it down into cases. So here we're putting a few things together. I've taken the contrapositive and then I've broken it up into cases. Okay, so now it's just time to write things up nicely. So if I can do that. Okay, so let's write it up nicely. So our proof, first thing we do is we tell the reader, hey, we're going to prove the contrapositive. So we'll assume that 3 doesn't divide n, because we're going to prove the contrapositive, so we assume the hypothesis of the contrapositive is true, that is 3 doesn't divide n. Then by Euclidean division, we know that n is 3a plus 1 or 3a plus 2. So we're explaining to the reader where our cases come from, and the reader can have some confidence that we've actually gotten all the cases. Okay? It's an important step in a proof by cases sort of proof, is to explain these are the cases, that's why they're all of them. Okay? So now we do case 1, n is 3a plus 1, so n squared is this, which is 3 times something plus 1, and so because I've written it as 3 times an integer plus 1, it's not divisible by 3. Case 2, n is 3a plus 2, n squared, compute things out. Again, I can write it as 3 times something plus 1, so again, it's not divisible by 3. Since 3 doesn't divide n squared in either case, the result holds, and we're done. Okay, I'm going to stop there. Thank you.